Okay, so again, today we are talking about similarity transformation. So this is all of sections 7-1 to 7-3. So those are the pages I had you rip out. Now, we'll probably use some of the problems in 7-1 to 7-3 for homework assignments. But again, today we're just taking just old-fashioned notes. I think they're easier for this section. So first we need to know what a similarity transformation is. Now, we have talked about some other types of transformations already. The other type of transformation that we already talked about was congruency transformations. Can somebody remind us as to what is a congruency transformation, or what are some types of congruency transformations? You guys remember doing transformations? What you got?
When it's rotation. When it's rotated.
Okay, so a rotation is a type of congruency transformation. What are some other types? Reflection. And one more. No. So you have rotation or reflection. No. What was it? I heard somebody say it. Translation. There it was. So reflection, rotation, and translation. Those were our three congruency transformations. And a congruency transformation was where the original pre-image and the new image were congruent. So a similarity transformation, let's go ahead and define that first. Similarity transformation yes. All right, our similarity transformation. For this one, our definition is the image and pre-image will be similar. Right? The image and the pre-image will be similar. Now, we also talked about our congruency transformations in terms of rigid motion, and our definition of that one went and talked about how the shape and size were. The shape in a congruence transformation had the same shape and the same size. What do you think is true about the shape and size in a similarity transformation? Will we still have the same shape? Yes. All right. So we have the same shape. Will they still be the same size? No. All right. So same shape, but different size. And we should actually be familiar with one type of similarity transformation already, because we mentioned it back when we did our transformations the first time. Does anybody remember the one transformation we talked about that was not a congruency transformation? Think about the eye, okay? So if you go to the eye doctor, what happens? Huh? Dilate. All right, yeah, a dilation. So, let's define one more thing before we actually define dilation. So we talked about how they're similar here. Now, in order to have similar figures, so they're the same shape but different size, I'm going to go ahead and define similar figures real quick. Similar figures are going to have angles that are congruent, but the sides, since they're not the same size, do have a relationship. Does anybody know how the sides of two similar figures are related? So angles are congruent. Sides are proportional. What does it mean to be proportional? Anybody know?
Same amount.
Same what?
Amount.
So, when you have a proportion, that means that you have two fractions or two ratios set equal. So, all of the parts, all of the sides are going to change by that same ratio. So if they're proportional, if you decrease one side by half, then the other side has to decrease by half. Right? If you increase something by 3, then the other side has to increase by 3. And when we're talking about similarity, we're multiplying. So the next word here that we need is dilation. Dilation. And a dilation, we already said it's a transformation. But what happens in this type of transformation? So what happens when you go to get your eyes dilated? They get bigger. Now, is a dilation only getting bigger? It could also get smaller. So, transformation that enlarges or reduces, shrinks would be a good word there too, all parts of a figure proportionally. So now, this ratio that we're using has a specific name. It's called our scale factor. And as far as variables go, whenever we talk about scale factor, the letter that's normally used, they can use some other letters, but most of the time they use the letter K to represent scale factor. Don't really have a good reason for that. It's just what it is. So, the scale factor is the ratio of the image to the pre-image. If we were to write this as an equation, we could say K is equal to, image goes on top, pre-image goes on bottom. Now, there are two types of dilations. Again, it's either getting bigger or getting smaller. And we have a name, a specific name for each one of these things. What do you think we might call it when a dilation increases in size and gets bigger? Think about, like, if you went, oh, they don't really have that anymore. Everything's online. I was going to say if you get photos developed, but if you go to online and order something from Snap-ish and want to get something bigger, what would you be calling that if you're increasing an object in size? What was that? Yeah, you're enlarging it. So it's an enlargement. So an enlargement is a dilation that increases in size. Now, if we talk about our scale factor on an enlargement, our scale factor will always be greater than 1. Because if the image goes on top and it's getting bigger, that means that the bigger number will be on top on our fraction. So it will always give us a value that's greater than 1. So then the opposite of enlargement, I already started writing it, is a reduction. So that's a dilation that decreases in size. Now, what do you think our scale factor is going to be for a reduction? All right, so it's going to be less than 1, yep. Now, is there a limit to how small it could be? So, yeah, it has to be bigger than 0. So it can't be a negative number, and it can't be 0. So it has to be between 0 and 1. Because if you multiply by 0, you wouldn't have a number, so that wouldn't work. You also can't have a negative scale factor. Now, could they say negative k? Yes, but the negative would be talking about direction then in that case, not the change in size. So now, the next thing we're going to do a little drawing here. So, in order for this not to run into the stuff up there, I make sure you have some decent space. If you don't think you have enough space at the bottom of the paper, then you might want to start off on the back. Right now I have about a quarter of the paper left down at the bottom of mine. But what we're going to do, we're going to make a triangle. And before we even start our triangle, we're going to do a point over here to the left side of our paper. And again, it can be completely random. It doesn't have to be in the same spot. Everybody's drawing will be slightly different here. And then somewhere in the first half of the paper, I want you to draw a triangle. And I would like you guys to try to use the same measurements that I'm going to give you. Everything that we're going to do with our rulers today, I'll use either millimeters or centimeters side of the ruler. I'm not going to do anything in inches, just to try to make it a little bit easier. So, now, I'm going to try and center this first line, but I'm going to make a 3 centimeter line. That's vertical. So I made that line 3 centimeters. All right. And I want to try to make a right triangle out of this. So again, it doesn't have to be perfect. So I drew a vertical line that's 3 centimeters, and I'm going to draw a horizontal line that's 4 centimeters. And by doing so, I should be able to make a triangle that has the dimensions of 3, 4, and 5. So if I connect these two, if you have the other two accurate, it should be roughly 5 centimeters long. Now, what I'd like you to do now is we're going to create an enlargement. So we're going to make this bigger. All right. So first thing, now this point was random, so everybody's going to be slightly different here. I'm going to measure the distance from that point to the triangle there. So to that top vertex. So on mine is roughly at 4.5. All right? That's 4.5 centimeters. Now, I want to double this triangle in size. So this point that I drew over here, what this is our center of dilation. So I'm measuring this distance because in order to double this figure, I am going to double the length that is away from that center of dilation. So currently this is 4.5 centimeters. If I double 4.5, what would I be at? 9. Now, on your paper, it's going to be slightly different because you picked a point at random, right? So, say yours is 4 centimeters. Well, then you'd be at 8 centimeters, and so on. Again, whatever number you have when you take that measurement, you want to double it. So, whatever this value is, I don't want you to actually draw this line. I'm drawing this to help you guys understand what it is we just did. So whatever this line was, if I call this piece X, whatever that measurement was, then this would be 2 times whatever that measurement is, right? whatever measurement you had here, and again, you're measuring it, double it, and put your other point. So now, we're going to do the same thing for the other 2 points. So, if we measure from that center of dilation to the next vertex, here this one's at 4.3 for me. So if I double 4.3, that'd be at 8.6. I'm going to put my next point right there at 8.6. Again, whatever your figure is, that's what you're using. You're going to double your lengths. I measured my last one. My last one is at 8.3. So, from 8.3, oops, I just moved it. If I double that, that'd be at 16.6. So, again, you're doubling the length each time. So that then you'll be able to connect your 3 points and you should have a triangle. Now, when you make this triangle, it should still appear to be a right triangle. Again, all you're doing is measuring the distance from, oops, I didn't mean to make that mark. All you're doing is measuring the distance from that point that's acting as your center of dilation and again, everybody's drawing is going to look slightly different. Where's your point? So, why would I recommend picking a point right about there? Yep. Work out fine. So now, measure that length. Point to that vertex. So that's roughly 3.1. It's right at 3. So then you go out to 6. You don't have to draw that line. I was drawing that line just to show what I was measuring, but just put a point there. That's 6 where you had it. You don't need this line. Go ahead and erase that.
It didn't hurt. All those times.
So now you do the same thing with the next point. So now you're measuring from here to there. Alright, go around. And you'll
Why
double
are
that.
those tiny things?
A triangle.
Ew.
Because I wanted to make that.
This is the original triangle, right? That's the original one. Make it the dimension.
Well, that's a whole other thing.
The original one I had asked.
No. Nope. I'm worried.
3, 4.
Shut up.
3, 4, 5.
What's 5 times 3?
That way when you double it,
Wait.
you should see a
What's 4 times
12?
But yeah, I feel like
I don't know.
How?
Because you're going to do that.
Thanks, man.
Only from this one. So,
Hell no.
this one's not from that point. Yeah, I started right redrawing.
12.
No point. Take a brain.
What is your triangle?
Whatever
I wanted to do.
There it is. Double that.
Why am I shit elevated?
So now, maybe together.
Makaya.
Alright, so.
He does not like that.
No, no, wait, try it.
Okay.
3.5. What's 3.5?
Is it to 7?
7. Alright, so put it
Why am I trying to work?
You can put your double dilation. Okay, so
How'd you do that?
I just would do use this way.
Wait, where is he? Where's the virus?
You don't buy my cheer shirt?
I do.
Do it.
A cheer shirt?
Yeah, you want to buy one?
Can you buy me one?
No.
If you buy me one,
Oh my god.
It's fine.
What?
Guys.
Yeah, guys, listen real quick. Shh. I had a good question. I was just helping Monica over there, and on hers, her line came through about here. That's fine. Everybody's drawing is going to look a little bit different. So depending on where your point is, the triangles might overlap. All right. In my last class when I did this, my triangles overlapped. It depends on where you put your point. So yeah, they're just doubling the distance for each one of those verses.
I'll show you how to do
You sure? You sure it's not thick? Are you sure?
What? I don't know that.
It's thick.
Look, how many points I have to
Yeah.
So we're trying to
You do not look like this.
Yes, I do.
You're straighten out a bit. Just a little bit.
You're down. Let's do this. We're trying to make this.
And you're not me.
His little curve.
There we go.
Look.
Good enough.
Now.
Bro, I'm straight out. I'm gonna tell her that. Just think. I know.
Ava. They're talking about you.
No, she's talking about you. She's talking about you.
Him and her.
Where does the third point come in?
That's messed up.
All good things, all good things.
All good things. But when are you?
Those two, this point here. So you gotta measure that length.
Where did your pink hair?
Idiot. Where's your pink hair?
Alright. If you have your new triangle, what I want you to do next is use your centimeter side of your ruler and measure the length of those pieces. So those three sides. If you already have a triangle, measure the length of those three sides. Now, they're not going to be perfect because anytime we use a ruler, it's not going to be perfect.
Quit touching my ruler.
Let him stop. Nothing weird, bro. Caitlin. Katie. Grabby. Grabby. I think I did it.
Alright, so now, measure those pieces. This will tell you how accurate your drawing was.
Oh, centimeters. Shut up.
We've been doing centimeters for time. Why would you change?
Sorry, guys.
Yeah, again, in centimeters, please. I'm not trying to teach you guys conversion in inches right now.
This paper is approximately 10.5.
Alright, so what should be true about all these pieces? What are you noticing?
They should be double.
They should be double. So if you measure it, and again, I don't know how accurate mine is, but that's pretty good, right? I got 6 centimeters here. If I do this side, I have 10 centimeters. If I do this side, it's not perfect, but it's roughly 8 centimeters. So, on here, again, we double the length from that center of dilation. That 2, what we're multiplying it by, that doubling, that's our scale factor. And if we compare the sides here, we should see the same scale factor. So if we go from image to pre-image, 6 over 3 is 2. 10 over 5 is 2. 8 over 4 is 2. So on this image, our scale factor, no matter which piece we use, let's say I just use the hypotenuse for a second, 10 over 5 gives me 2. Which again, it doesn't matter which piece you use, it is 2 in every case, because that's essentially what we were multiplying by. Whenever we multiplied this distance by, that was our scale factor. That's our K. Now, could you also do the same thing with a reduction? Yeah, right? So you could have also reduced this the same way. If we cut this length in half, if we cut this length here in half, what would happen to all the sides of this triangle? They'd also be half, right? So again, now you guys don't need to do this part. You already did the enlargement. I don't need you to do the reduction. But again, we have that 4.5. If I split that in half, it'd be 2.75. Wait. No, that's in the wrong spot. Hold on. Not 7.5. I misspoke. 4.25. If we go to this one, which was at 4.3, half of that would be 2.15. If we went to this one, which I said earlier was at 8.3, that would be at 4.15. And my triangle would look like this. But again, they have to be lined up like that in order for this to work. So again, 1.5, this would be 2.5, and this would be 2. However you multiply or divide that original measurement is the same thing that happens to all of the sides here. So my scale factor going backwards here would be 1/2. Now, you can do this without a coordinate plane. You can also do this with a coordinate plane. So the other thing that we need to look at is on a coordinate plane. So let me, again, you can either flip your paper over or go to a new sheet, whatever you want to do. I'm going to draw a coordinate plane real quick. I think I might change my values slightly from my last class. But
I'm not on.
you don't have to be this accurate. I'm just marking off every half centimeter to make this easier for me. I don't even know. I just drew a line. I did 8 centimeters long and marked off every half. I'm gonna do same type of thing on this side. Now, I'm gonna put it in the first quadrant to make it easy, so it doesn't have to be. You don't even have to mark all of the other quadrants. All right. So first point that I'm going to use is 2, 2. Let's use a different color. So I got a point at 2, 2. I'm going to put a point at 6-2.
Wait,
4,
how long is
5,
that?
6. And I'm going to put a point at 2-4. So if I was to draw this triangle here, just connect my dots. Yes.
How long is that?
How long is what? Well,
Cut it, right?
doesn't really matter. I went to 6-2. The biggest I would need for this is to be able to go out to 9 on the x-axis and 6 on the y-axis for the numbers I just used. All right. So, I want to find the points of the dilation of a scale factor of 1.5 centered at 0, 0. Now, centered at 0, 0 is what makes this the easy part. If it's centered at 0, 0, all you actually have to do is take these numbers and multiply them by your scale factor. So I have a point at 2, 2. If I multiply 2 by 1.5, what do we get? It's 2 times 1.5. Not everybody at the same time. 3. Yeah, 3. So 2, 2, and I'll be at 3, 3. Then if I take 6.2, and multiply each of those by 3, well, 6, sorry, not 3, by 1.5. 6 times 1.5 is now what? 9. So this point is at 9, 3. And if I take, well, again, I had 2, so I already know 2 times 1.5 is 3. 4 times 1.5 is 4 times 1.5 is 6. So this is at the point 3, 6. And again, if I look at the dimensions for this triangle, they should all be increased by that same scale factor. So look at this side. Here, this length was what in units? This is currently 2 units, right? How long is this? 3 units. It increased by 1.5. This side, 1, 2, 3, 4, 4 units. This side is now 6 units long. So again, they have that same scale factor. So again, the scale factor for these two shapes is 1.5. Now, I already had you guys rip out the pages. Your homework assignment that I want you guys to try tonight is from page 297 to 322. Oh, sorry. That's what I had you guys rip out. I'm going crazy. I copied the wrong thing now. That's not your homework. That's the pages I had you rip out. The homework, my bad, was page 302. Numbers 1, 2, 5, 6, and 7. 1, 2, 5. All right, so it's 5 problems.
I can do that.
So again, try those 5 problems, and then I would recommend starting to work on the review as well. All right.
Wow. Which one's the big one? Or which one's the real one? Which one's the image and which one's the pre-image?
Okay. Guys, remember, when we're talking about an image and a pre-image, the image, the new figure, is the one with the primes on it. Right? One of those has primes, right?
Okay, yeah.
So again, the new figure is the ones with the primes on it.
Okay, my bad.
Hat.
You get it.
We do that in the